Good morning, students. It's Charlie Arbuso, your chemistry teacher again. We're going to work on the notes today, 75 to 96. That's about the end of it. Then there's just review and, of course, the review lab. We have a whole bunch of practice slides, too, that we're going to go through. We're going to look at what's called molecular compounds. Today, we've started with simple ionic compounds, monoatomic ions. That's group 1 and group 2 metals and aluminum. They make +1, +2, and +3 cations. We've also looked at the anions and non-metal side, group 17, 16, and 15 that make -1, -2, -3 anions by gaining electrons that come from the metals. The ions, they transfer their electrons perfectly, and the compounds that form are, of course, neutral. Then we looked at the metals in the middle of the table, and many of them make more than one kind of cation because they can. And in order to deal with that in a name sense, they follow the same rules. Metals first, non-metals second. The non-metals become IDE endings as well. But if there's more than one positive cation, we have to use a Roman numeral to match the ion charge. Then we looked at what are called polyatomic ions. Those are small or medium-sized groups of atoms bonded together that can either be positive cations or negative anions, and they're found only on table E. They follow the same basic crisscross rules. Sometimes you need parentheses if there's more than one of those multiple groups, and you never change their names. Today, we're going to look at what's called molecular compounds. And a molecular compound is a compound that has no metals in it, something like carbon dioxide or H2O water. There's no metals, and they actually are going to bond in a very different way. They don't form ions. There are some positive and negative numbers, but they are not ions. And they, instead of transfer electrons, that's a key indication. Metals and nonmetals transfer electrons from cation to anion. The molecular compounds share electrons. Completely different way of bonding, completely. And we'll learn about bonding another day. But these compounds form into molecules, not crystal structures, not ions. They form into molecules, and you're going to need the periodic table. We're gonna deal with them now. There are 22 non-metal elements. 6 of them are noble gases, so they're out. So out of that, what is that? 22 minus 6. That's 16. Out of those 16 atoms, there are literally millions of compounds, millions of different kinds of molecules. There's the bell. I'm at school. Millions of kinds of compounds. We will name a fair number of them. There's a lot of patterns, and it's not going to be that hard. So here we go. Get out your notes. Get out your periodic table. Ionic compounds form when positive cations and negative anions combine in a proper ratio with each other, and the attraction is because of opposite charge. Except for the weird ammonium, that's a table E polyatomic, which is NH4 +1. Every single cation is a metal. Ammonium is our lone example of an exception to that rule. It's a polyatomic cation. Now, a molecular compound, which is what we're really going to talk about today, there's no metals. So instead of the first element in the formula being a metal, it has to be a nonmetal. Molecular compounds form when 2 or more nonmetals bond together in the proper ratios. In molecular compounds, there are no ions and no ionic bonds. There's no ions. When they form into a compound, the simplest or smallest part is called a molecule. A molecule is the smallest part of a molecular compound. Now, a water molecule is called, well, it's H2O. And the oxygen atom is a little bit bigger than the hydrogen physically in size. And the 2 hydrogens bond onto the oxygen, and they make that Mickey Mouse looking little thing there. Now, that's like a cartoon of a single molecule. In this glass here, literally there are bazillions of water molecules, mega, millions and billions and trillions. There's so many because molecules are so little. Each molecule is independent, and they're sticky, they're touching, they move all over each other because they're a liquid, but they're actually independent. Whereas in a salt, it's a repeating crystal pattern that sort of everybody is locked together, and in a molecular compound, they're not stuck in rigid patterns. Now, these are molecular compounds, and you know every one of them. We're going to go through their names just so you can be reminded that this is not so scary. First of all, there's no metals. Now, going across the top row, you know these, right? CO2. You knew this before you met me. Carbon dioxide. The middle one on the top is called carbon monoxide. That has one oxygen. And the third one, that would be called hydrogen monochloride. Now, some of you might think, oh, wait a second, I saw that in biology. That's the stuff in my stomach called hydrochloric acid. Now, in fact, HCl, when it's dissolved in water, will make an acid called hydrochloric acid. But to name the compound properly, when it's not dissolved in water, it would probably be a gas unless it was super cold. At room temperature, HCl is a gas. HCl will be called hydrogen monochloride. Now, in the second row, you probably know these, right, as well. NH3, that's that stuff when you're in an MMA match and somebody kicks you, knocks you down, kicks you in the head, and you're knocked out. They make you smell this stuff. And two things can happen. Either the ammonia, that's what it is, ammonia will make you cough and gag and wake up, or they kicked you too hard, because if it doesn't wake you up, it's really bad, because ammonia is pretty annoying to this, you know, a little bit will bother you. A lot would be really bad too. CH4 is methane gas. Methane, you could also call it carbon tetrahydride if you want to be cool, but it's got a common name. We call it methane. It's kind of an organic name. H2O, of course, is water. Water also could be called dihydrogen monoxide if you want to sound hoity-toity. And that last one is called octane. Octane is an organic molecule. It's also known as gasoline. You put that in your car. Most of the gas you put in your car, most of it, I think it's like 89 or 92% is octane. They do put some other stuff in there so that farmers can turn corn into ethanol. Ethanol is actually the alcohol you could drink, but not when it's dissolved in gasoline. That burns as well. But octane is a hydrocarbon gas that burns. It's kind of like methane, made of carbon and hydrogen only, burns like mad. Very dangerous. Never play with gasoline. It really is terribly explosive, terribly. And that's why just a little bit of it makes your car go so far. If you think about it, tank full of gas, you can take 4 or 5 people, 300-400 miles. I mean, it's a lot of power packed into that little liquid. But importantly, there's no metals. The first letter of every symbol, of every formula, starts with one of the 16 letters on the periodic table that's a non-metal. Hydrogen, carbon, and the rest of them, not the noble gases. Now, the bonds that hold this stuff together are non-ionic bonds because there are no ions. The bonds are called covalent. That's a vocabulary word in blue, covalent bonds. Co means to share, like you're the co-captain of the ski club. That means you and your friend are in charge of getting everybody to sign up. Hopefully we'll have a ski club this year. Valent, the valent part, means the outermost electron layer. You're going to share only your outermost electrons. You don't share the inside electrons. They don't bond, only the outermost. So a valence curtain is that little trim curtain that goes over the top to cover the rod. Some people like to have their curtains hanging magically on the walls. Like they're not curtain rods here. We're going to hide them with this valence. They're kind of pretty, but a valence is sort of the outermost kind of curtain. In this case, covalent means share your outermost electrons. Just like I said, sharing your outermost electrons. We'll learn all about covalent bonding another day. That's just a name. When 2 or more ions bond, they make an ionic compound, ionic bonds, and they make what are called formula units. The particles themselves, you don't ever get an sodium chloride. You don't get a sodium chloride unit. They're not molecules. The ionic compounds, because they exist as a crystal, unless I suppose you dissolve them in water and then they all separate anyway, you never get just one. You can't have NaCl single unit. Whereas water, if you evaporate it, the water molecules are independent of each other. You get individual molecules. This is just a vocabulary word that I like to make you laugh. But the word is actually formula unit. You can get the idea of a single unit. You can have NaCl, one Na, one Cl ion, but not really. You can't have it in your hand. But the smallest concept of an ionic compound is called the formula unit, which we abbreviate as, I guess I have to write it, Fu, right? FUs. NaCl doesn't come in molecules because it's ionic. It's a crystal dissolved in water. Ionic compounds don't make molecules, but molecular compounds do. Now, these are the names. The easiest way to remember the rules is if you can remember 3 molecules. And honestly, you should write them down. Here's my periodic table. I don't know, let's see. Maybe right up here somewhere in this empty space. Molecular compounds. CO, CO2, and H2O. And if you can remember the 3 compounds, formulas, and names, it will remind you of the rules. So let's go. CO, carbon monoxide. CO2, carbon dioxide. And H2O is not just water, it's called dihydrogen monoxide. Now, how do we name molecular compounds? We have 2 rules, the first name and the second name rule, but the first name rule is a little fancy here. The first name rule, you say to yourself, is the first part of the formula, is it a single atom or is it a multiple? If it's a single atom like CO and CO2, there's just 1 carbon. If it's a single atom in the front, just say the name of the atom, carbon, right? It's not monocarbon. You don't say monocarbon dioxide, that's crazy. You just say carbon. So if it's a single atom, you just say the name of the atom. But if it's a multiple, like in water, which is H2O, you have to have a prefix. That's called dihydrogen. You have to say how many. Either it's 1 or it's how many. Now, the second name rule, you always get a prefix. So if there's 1 oxygen, like in carbon monoxide, you have to say 1 oxygen. If it's carbon dioxide, there's 2 oxygens. And if it's water, which is dihydrogen monoxide, the second name, you always get a prefix. So we're going to use what's called prefix names for the molecular compounds. And there's 2 rules. You have to write these down. You might even write them on your periodic table. But really, if you remember CO, CO2, and H2O, you will always be able to remind yourself of the rules. It's either a single atom or a multiple atom first. So you either get a prefix or you don't. And the second name, you always get a prefix, always. Now, these are the prefixes. You have to write these down too. Maybe down here. I don't know, where's this thing here? Maybe down here. You have to remember them. You probably know some of these. Mono is 1. Di is 2. Tri, like a tricycle. Now, quadricep is your leg muscle. It's got 4 parts. Tetra is the prefix in Latin. Tetra for 4. Penta, like a pentagram, if you're a witch, right? You have a pentagram. Hex is 6. Sometimes the Amish people have hex signs. There's 6-pointed stars to keep the evil spirits away. Hepta is 7. Octo is 8, like octagon. A stop sign is an octagon, 8-sided octagon shape. Non or nona, N-O-N-A, for 9, right? And deca. Like sometimes this class takes a decade, like 10 years. Deca is 10. Actually not. It's going to take like 30 minutes or something today. You have to memorize these. I don't know what else to say. Figure it out. Make some flashcards. Learn to count 1 to 10 in Latin prefixes. So we're going to go through a whole bunch of these. We'll do the yellow ones first. Now, there are 2 rules. First name rule, second name rule. I'm going to go through them quick. HF. First name is singular, no prefix. H is called hydrogen. Second name always gets a prefix. Fluorine, we're going to change to fluoride. So it's going to be hydrogen monofluoride. Hydrogen, oh, look at that. The SF6 on the top right in white becomes SBR6. Who knows what it'll be by the time we get to the end. Hydrogen monofluoride there on the left. The next one, CS2. 1 carbon, so it's going to be called carbon. And now we have 2 S's. How do you say 2? Di. How do you say sulfur? Sulfide. Carbon disulfide. Look at that. Bing, we got it again. SO3. S is sulfur. There's a single one, so we only say sulfur. How do you say 3? 3 oxygens. Trioxide. Sulfur, trioxide. CCl4. 1 carbon in the beginning, so it's going to be called carbon. How do we say 4? Tetra. Carbon tetrachloride. Look at that beautiful thing, carbon tetrachloride. PF5. P is one of them, phosphorus. Phosphorus, how do we say the which number? Penta. Phosphorus pentafluoride. See how easy this is? It's a single name in the front. You just say the name of the atom. And if it's a multiple, like some of them coming up are multiples, right? Then you need a prefix. The second name, whether it's one or more, always gets a prefix. And it's IDE, of course. It looks like it's going to be SBR6. We'll see what happens. I might have to change that first one from SF6 to SBR6. So here we go. SBR6, 1 sulfur. And to say 6, we say hexa, what? Hexabromide. Sulfur hexabromide. This one's tricky, right? Oops, we got stuck in a hard one now. How do we say 7 again? Hepta. Now, the first name, we don't change to IDE. We just got to say 7 nitrogens. Heptanitrogen trichloride. These are a little tricky, right? Heptanitrogen trichloride. This next one, we got another prefix in the front name. We have 2 chlorines. We don't change chlorine. It's a first name. We never change to IDE unless it's the second name. So this is going to be dichlorine octoxygen, or I'm sorry, dichlorine oxide, 8 oxygens. Octoxide. It's a tricky one too. 4 iodines and 9 oxygens. So we're going to have tetraiodine non-iodide. I said that wrong. Tetraiodine non-oxide, because there's 9 oxygens. And honestly, I can't see the last one. I got something blocking my view. And let's see if I can move that up. Oh, there it is. N2F10. 2 nitrogens and 10 fluorines. This is what we call dinitrogen decafluoride. Look at that. Woo! Dinitrogen decafluoride. So listen, here's some wacky names. You have nothing to be afraid of. You have 10 prefixes. The first name either gets a prefix or it doesn't, and the second name always gets a prefix, and it ends in IDE. Don't change the first name, you might add a prefix. Second name changes to IDE. There's only 16 atoms that can do this, right? The 16 nonmetals, not including the noble gases. So what that there's millions of compound combinations? You can name them now. Well, you can name them up to 10. Right? They get bigger than that, but you can name them up to 10. So here we go. We're going to go in reverse. We're going to write formulas. Phosphorus tribromide. Now, if your first name is phosphorus, you don't have a prefix, there's only one. So just write the letter P to start. P. And how do we do tribromide? Bromine is Br, and we need 3 of them. So it'll be PBr3. All right, look at that. PBr3. I got 2 of them in a row. I got black and blue. Feels like we're getting beat up. PBr3, phosphorus tribromide. Next one is called diphosphorus. Don't get excited with all these letters. Di means 2. Phosphorus is P. P2, diphosphorus, and then next, trioxide, O3. P2O3, diphosphorus trioxide. Oxygen difluoride, I always make a joke, right? Oxygen is just O. And difluoride, that means 2 F, so it'll be OFF or off. No, we don't write it that way though, right? Difluoride would be OF2. OF2. Oxygen, no prefix because there's only one of them, difluoride. Dihydrogen monoxide, 2 hydrogens, H2, 1 oxygen. You knew this one, right? Woo! Water, W-A-T-A. Yes, you can do this next one. Yes, you can. Nitrogen, N. Monoxide means a single O. No, yes, you can. Yes, you can do this. It's not hard. NO, nitrogen monoxide. Carbon tetrafluoride. How many carbons? Just 1. So write capital C for Cookie and Charlie. Capital C for carbon. 4 Fs. Bada bing. You guys are professionals at this. We got a little bit more to go. What do we get up to? 96? We're making a lot of progress. Name these compounds. I'll be quiet for a minute. Let me have some seltzer. Today we got mandarin orange seltzer. The can's aluminum. It's not going to ever be in a molecular compound. But most of the stuff inside is water, H2O. There's a little touch of carbon dioxide. That's another molecular compound. And a little tiny hint of orange flavor, which is actually chemically speaking, it's an ester, E-S-T-E-R. It's a fairly complicated molecular compound. We'll learn about them in organic chem. Esters tend to smell or taste really, really good or bad. Banana is methylhexanoate. Strawberries, blueberries, a lot of esters. Plants know how to do that chemical reaction to make esters. Here we go. NO2, 1 nitrogen. Nitrogen, 2 oxygens. Nitrogen dioxide. Look at that. Bada bing, nitrogen dioxide. CI4. C is carbon. There's only one. So it's carbon. Carbon, how do you say 4? Tetra. Carbon tetraiodide. N2O. We saw NO before. This is N2O. It's a little different. There's 2 nitrogens up front. We have to say dinitrogen, and the second name always gets a prefix. Dinitrogen monoxide. SO3. This should probably roll right off your tongue right now. Quick, quick. Say it. Say it. Say it out loud. Don't say it. Nobody's there. Nobody's looking. Just say it out loud. Sulfur trioxide. You can do it. Just try. This next one's a little trickier, right? Because you got 2 prefixes. Don't be afraid. You're all by yourself in your room. Say this out loud. I'm waiting for you. I can't hear you. Just say it. 2 nitrogens, 5 oxygens. Ready? Dinitrogen pentoxide. You can do this. HCl we talked about before. It's not hydrochloric acid because it's not dissolved in water. This is a molecular compound made of nonmetal bonded to nonmetal. So it's not an acid because it's not a mixture in water. It's just a compound. 1 hydrogen, 1 chlorine. Hydrogen monochloride. You could roll back. You could do these again, right? Good practice. Now, tables K and L. For no good reason, in the middle of this, we just stick this in here because I don't know why. I just picked the spot to introduce this so it'll kind of come to us when we need it. But table K and L. See them? K and L. Table K are the acids. Acids are a separate part of chem, kind of like organic. It's kind of cool. Man named Svante, that was his first name. A man named Svante won a Nobel Prize for describing how acids and bases worked and some theories behind them. And actually, as casual as acids and bases are, there's a bunch of theories. We're only going to learn 2, but there's a bunch of how to explain what is an acid and how does it work. Hydrogen's really weird, and hydrogen's involved in all the acids. If your first letter is an H, and if you go into water and you can ionize, you're an acid, right? And the base is the opposite. The base is literally the opposite of an acid. It balances it out. Bases have what are called hydroxides. Remember we looked at that on table E? We had that cool polyatomic anion called hydroxide, OH negative one. See if you can remember this one day. Hydrogen, when it's in water, can strangely make a hydrogen ion. That's what makes it an acid. So if you have an H positive 1 ion and it meets up with a hydroxide OH negative one, you have H and OH. And if you put it together, you get HOH or H2O. The acid and the base turn into water. How cool is that? So we have acids. There are the names. They're all aqueous. That means they're all dissolved in water. If there's no water, they're not acids. If you breathed in, which would be terrible, breathed in a gas called HCl, when you breathe that gas in, you would not be breathing in acid, but when it touched all the wet inside your body and your lungs and in your throat and in your mouth, it would turn to acid to become terrible really quick. Acids are on table K, and underneath them are the bases, the opposite. And there's a bunch more bases. I'll give you some more information later, but that's just a short list of bases. There's a lot of bases and a lot more acids. So there they are. They exist, and there are their names. You can look them up. Also, number 90, 7 elements on the periodic table are called diatomic. Now, when they bond together in their pairs, because they're a little too afraid and too unstable to be individual, we call them diatomic elements because there's 2 atoms of the same bonded together. They make molecules. That's why they're in this part of the course right here. They're molecular, but they're not compounds. They're elements. They're just diatomic elements. And we will remember them by saying this word out loud. Now, I'm going to say it twice. You have to say it a couple times. Hunkelbrief twins. The Hunkelbrief twins stands for the H2, O2, N2, Cl2, Br2, I2, and F2. You got hydrogen, oxygen, nitrogen, chlorine, bromine, iodine, fluorine. There are 7 Hunkelbrief twins. When they are pure, when you have pure nitrogen, like the nitrogen in the air is nitrogen N2 molecules. Most of the air, 74% of it or so, is nitrogen. 20% or 18% is oxygen, is O2. That's what we breathe. When I fill up a balloon with just hydrogen gas, it's H2. There's no H atoms. They're too unstable. Bromine, iodine, fluorine, they're also diatomic, Hunkelbrief twins. All right. How do we decide what's the ratio of atoms to atoms? Right? Remember before we had the molecule NO, and then we had N2O? Actually, there's 5 different nitrogen-oxygen compounds. And how come water is H2O, but it's not HO2? We're going to learn about what's possible and what's Kim possible. Remember that show? No. What's real and what's not real. One interesting thing is when I'm watching a movie or something, science movie, and they'll say something like, you know, pass the hydrogen trioxide. It's like immediately it just falls apart for me. Unfortunately, when you know stuff, you can't get fooled so much. You can't believe people living in outer space if they're making up molecules. We're going to now see what's possible and what's not. You're definitely going to need your periodic table, right? You got to have it. You're going to put your fingers in the boxes. Get this out right now and put your thinking hat on. In the key, we have what's called selected oxidation states. Those are the positive and negative numbers in the top right-hand corner. Now, I have to tell you, we did talk about these positive numbers for the transitional metals. For the metals, they're all positive, right? From scandium out to polonium, we only have positive numbers in the middle of the table. And those numbers are the types of cations that those metals can make. That is true. And unfortunately, we don't have a table somewhere else called selected oxidation states. It wouldn't be a big table, but we could have a list of selected oxidation states. And if it wasn't in the same place on the periodic table, in the top right-hand corner with positive and negative numbers, you wouldn't get so mixed up. But for the non-metals, we have something called the selected oxidation state. Now, this is not ions. This is positive and negative numbers. An oxidation state is very complicated, but what it is a system of numbers that allows you to just look at the periodic table and figure out what is possible and what is not possible as far as molecular compounds. So there's 2 things going on. If you're a transitional metal and you only have positive numbers, those are the cations you make. But for the selected oxidation states, for the non-metals, we're going to use them not as ions, just as positive and negative numbers, and we have to combine them so that the positive and negative numbers we use in some ratio sum to 0, and if we can come up with compounds that sum to 0, we can actually figure out what compounds are possible. I talk too much. Let's just do this. We're going to write down all of the oxidation states for hydrogen and oxygen. So if you look in the H box, hydrogen can make a positive 1. I can't do this. This is so crazy. Positive 1 and negative 1. And oxygen only makes a negative 2. When oxygen makes an anion, it makes a negative 2. It's not an anion here. This is a molecular compound we're working on. Now, once we set this chart up with all the oxidation states that are listed, and we have done that, hydrogen has 2 oxidation states, oxygen only has 1 oxidation state. We're going to start, and very slowly, we're going to do this. I'm going to actually draw on this because I can't manage this any other way. Let's see, we're going to draw a line. We're going to look at this first oxidation state of hydrogen, which is positive 1, and then we're going to do the negative 2. If we would have a positive 1 for hydrogen and a negative 2, if we're going to look at these 2 oxidation states, when the positive and negative are opposite, they can cancel out. Now, we can't cancel this out in a 1-to-1 ratio. That would not work. But if we had 2 hydrogens, we had positive 1, that would balance in negative 2. So what's going to happen is we can have in a 2-to-1 ratio, H2O, which is in a 2-to-1 ratio, That is possible. So that means this compound, H2O, we know that's water, but H2O is possible. That is a compound that hydrogen and oxygen can make. That's a molecule that it's able to form. Now, if we look at this one, let me change color. If we look at this one, a negative and a negative, and no matter what ratio you get in, they're never going to balance. In this case, you know what I'm going to do? I'm just going to say, you know what? This one doesn't work, right? Doesn't work. So in this case, the -1 oxidation state will not work with oxygen. There's literally only one hydrogen-oxygen compound that is 2 hydrogens to 1 oxygen. That's the formula, H2O. That is the only hydrogen-oxygen compound in the universe. Okay? No others exist. And how do we know that? Because by using the selected oxidation states, we can figure out what ratios are possible and what ratios are not possible. If we had some other thing, let's say we have hydrogen and I do O3. Hydrogen trioxide, because, you know, I could say that, hydrogen trioxide, following the naming rules. Is this possible? Well, let's see. We have 3 oxygens, right? 3 oxygens, and each one is -2. -2, -2, and -2. That means the oxidation side of the oxygen sums up to -6. The question is, does hydrogen make a +6? Question mark. Because in order for HO3 to exist, hydrogen would have to have a +6 oxidation state. And all that means is scientists have figured out this number system. That's what this is. It's nothing secretive. These are the numbers that work and don't work. Does hydrogen have a +6 oxidation state? Look, I'm pointing with my other hand. +1, -1. No, this is not possible. And that means this is not possible. You can write it, but it doesn't work. The oxidation states determine what's possible and what's not possible. All right, let's see about moving ahead, and we'll do another one. The +1, -2, when they're opposite charges, we can figure out the ratio to make them work. But the -1 and the negative, no ratio, we have to skip that one. That means that -1 is for when hydrogen bonds to something with a positive oxidation state. There's a lot of other atoms to bond to. The only possible outcome is in a 2-to-1 HO. It's called water, H2O. Perfect. Now, the next one we're going to do is all possible carbon and oxygen compounds. All possible ones. Now, the selected oxidation states are not ions. They're not. Now, carbon, I'm looking right now. Let me get my pen back, and I'm going to go with a nice color this time to really stand out. We'll go with blue. Carbon makes a -4, a +2, and a +4. And oxygen only makes a -2. Now, where the heck did these numbers come from? Here's the carbon box. Look in the carbon box. See the top right corner? We get -4, +2, +4. And look at the oxygen box. Only a -2. These are not ion charges now. These are the oxidation states. We're trying to figure out what are the possible carbon and oxygen compounds. We have to use the oxidation states. One oxidation state from carbon and one oxidation state from oxygen. And is there any way to make the ratio balance to 0? Positive and negative sum to 0. So we will do this now as soon as I change color, because I want to be cool. -4 and -2. There actually is no way in any ratio to make a negative and a negative work. So the first thing we're going to do is we're going to say, you know what? This particular oxidation state for carbon doesn't match up with oxygen. There's no way to make that one work. Well, we'll skip that one. Doesn't matter, right? Now, if we look at this +2, if you have a carbon with a +2 oxidation state and an oxygen with a -2, we can get it going on in what I would call a simple 1-to-1 ratio, right? Or CO. And what do we call that stuff? Carbon monoxide. And actually, that's a gas. It's a poison gas. You don't want to breathe it. Carbon monoxide. That's possible. And now let's look at the next one. What if we use a +4 with a -2? Is that got one going on? Well, if it's a +4 and a -2, 1-to-1 doesn't work. But if we had 1 carbon and 2 oxygens, if we had a 1-to-2 ratio, 1-to-2 ratio, we would have a +4 and a -2 and another -2. That would actually work. And that, of course, would be C with 2 oxygens, which would be called CO2. And you know that, of course, is carbon dioxide. Now, based on our selected oxidation states, the only 2 possible carbon-oxygen compounds in the universe are either carbon monoxide or carbon dioxide. There's no more. We can't have carbon trioxide or pentacarbon decaoxide. None of those are going to work. CO2 and CO, based on these oxidation states. These aren't ions. These are molecular compounds. No metals, no ions. And we use what's called the selected oxidation states in order to figure out the compounds that are possible. So there we go. We write them down from the periodic table. And then the first one we cancel because there's no way to make it work. Negative and negative never can sum to 0. And the other 2, either in a 1-to-1 or a 1-to-2 ratio, and we name them. If it's 1-to-1, the first atom's carbon, we just say it. The second atom gets a prefix, monoxide. And then the last one there, single carbon and a double oxygen, so it's carbon dioxide. Those are the only 2 carbon-oxygen compounds in the universe. Last one, nitrogen and oxygen. Now, this is the biggest one. Honestly, it's probably the biggest one on the table. Nitrogen makes 8 separate oxidation states. Look at nitrogen here. Can you see it? It's got 8 freaking oxidation states. Oxygen only has 1. Let's write them in. I can't write them by hand. Look at this. -3, -2, -1, and +1, +2, +3, +4, and +5. Nitrogen has the most oxidation states out of any atom on the periodic table. And oxygen only has 1. We have to be methodical, right? There's a lot. It's going to be easy to get lost here. So we're going to be very methodical. We're going to get the pen going here, and I'm going to write again in another, let's see if I can find another new color. We'll do nice dark green. Negative and -2. No negative and negative can ever go together. So the first oxidation state for nitrogen, we're getting rid of that one. -2 again. Negative and negative can never sum to 0, and -1. So the first 3, look at this, we're making good progress. The first 3 we just throw away. Those are for when nitrogen might bond to something with a positive oxidation state. But when it bonds with oxygen, oxygen has 1 oxidation state. Those first 3 for nitrogen are, all right, we'll use them another day, right? I'm wearing my sneakers. I have a pair of fancy shoes at home. I can't wear them both on the same day. These 3 negative oxidation states are kind of like my shoes. I'm not wearing them today. Now, not to come to school, right? I'm bonding with oxygen today. I'm not going to use those. I could use the other ones, though. Now, we're going to try not to make this too messy. When we have a +1 and a -2, in order to balance this to 0, we're going to need 2 +1s. So it's going to be in a 2-to-1 ratio, or it's going to be N2O. That's our first nitrogen-oxygen compound. Okay, now let's look at this next one. What about when it's +2, -2? Well, that's going to balance in a different ratio. That's going to balance in a 1-to-1 ratio, and that formula is going to be NO. So that's our second nitrogen-oxygen compound. Now, what happens if we use the +3 and the -2? You got to think a little bit. If it's +3 and -2, you're going to need 2 of the positives and 3 of the negatives. You're going to have +6, -6 to balance. So to do that, you're going to have to do that in a 2-to-3 ratio. And what is 2-to-3? That means N2O3, right? Because if you have 2 positive 3s, that's a total of +6. If you have 3 negative 2s, that's a total of -6. And when they add up to 0, that means it works. Now, this is the actual hardest one. Mathematically, oops, I hit a bump on my mouse. Here we go. Here we go. If we start out with a +4 and a -2, we're going to have to +4, we're going to need 2 -2. So this is going to be in a 1-to-2 ratio. 1-to-2. So this is going to be N, 1 N, and 2 O's. NO2. That's a 4th separate nitrogen-oxygen compound, and we still got one more. If we use the +5 oxidation number and the -2, this is going to have to be in a 2-to-5 ratio. Now let's talk about how the heck I knew this. If it's +5, if we have 2 of them, that's +10. And the oxygen's a -2, so we have 5 of them, -2, -4, -6, -8, -10. So +10 by getting 2 nitrogens, -10 by getting 5. And so this, of course, would be N2O5. I'm supposed to make that a little closer. There's a little bit of a gap in here, right? But it's hard to write with a mouse. I'm getting old. I don't know. These are the 5 possible nitrogen-oxygen compounds. There's only 5, but there's 5, and now we have to name them. So let me clear this up. We'll get this typing going, and we can see it a little clearer. So look at this. The first 3 nitrogen oxidation states we cross out, but then 5 in a row. I use different dots so you can follow it. The red one, N2O, is called dinitrogen monoxide. The green one in a 1-to-1 ratio is called nitrogen monoxide. The black one is in a 2-to-3 ratio. It's called dinitrogen trioxide. The blue one is in the opposite of one before. It's 1-to-2 now. And, ooh, look at that. Look at that. There's a boo-boo. I got to fix it right now. It's going to be nitrogen. This is a dioxide, and this is a 2. Who made this? I spelled this wrong, too. Dioxide. Dang. Who's in charge of this here? Bring me the man in charge. Somebody's got to pay for this. Slide. Oh, it's still working on saving. This is a giant slideshow here. Woof. Boo-boo. Look at that. 1-to-2, nitrogen dioxide. And then the final one, 2-to-5, would be N2O5, dinitrogen pentoxide. That's a lot of chem. All right. Oh, I guess we got one more. I apologize. F and Br. This is it. 96 is the last one. F and Br. So F, fluorine, only has 1 oxidation state. Bromine has a few, right? Bromine's got 3 of them. So let's see what they look like. There they are. I'm going to give you a minute. Figure this out. See if I get my pen back. So F, -1, Br, -1. The Br, -1, we're going to cancel, right? Because a negative and a negative is never going to go together. When F, -1, and Br, +1 go together, that has to be in a 1-to-1 ratio, or we're going to have the formula F, B, little r. And this one, oh, we got a 5. That's a cool one. When it's -1 and +5, we're going to need 5 -1s to balance with every +5. So this is going to be F5 Br. Now, these oxidation states, these are a system of numbers that scientists have figured out to put down on paper so we can figure out what combinations are possible. It's a little more complicated than that, but we don't have to worry about it. It's not going to be more complicated for us, right? We got the 1-to-1 and the 5-to-1. Fluorine monobromide in a 1-to-1 ratio, or we have pentafluorine monobromide. And I said there at the bottom in black, the negative and the negative cancel to 0, so we have to skip that pair, right? We just crossed out the BR. These are not ions. Fluorine, when it makes an ion, is a -1 ion. It's not an ion here. This is a molecular compound. The two most important things you got to know. If your first symbol or name is a metal, you're ionic, and you follow a set of rules. If your first symbol or name is a non-metal, then you are molecular and you use prefix names. Ionic compounds transfer electrons, molecular compounds share electrons. So we have a lot of different naming systems. We got the simple ions, we got the transitional metal ions, we got the polyatomic ions, and now we have the non-ions, the molecular compounds. But that's it. Now there's going to be 3 more slideshows, Zooms to watch. Big slideshows, formula after formula after formula. It takes practice. It's not hard. You can write them down as we go, but we're just going to practice, practice, practice. So you watch the rest of these slideshows as soon as you can. The better you are at doing this, the easier the rest of the year is going to be. It's a chemistry class. You have to be able to read symbols. You have to be able to write symbols. You have to know why FBr is possible, but FBr2 is not possible. And the reason is because of the oxidation state system that's been developed. Peace, love, and chemistry. Thank you for watching. Over and out. Let's see about turning this off. End.